Alright, so let's take a look at January 2011, Unit 4, Section B. Got the Hubble telescope, and it has a time period of 97 minutes. So, first thing, to get the angular speed, we do 2 pi divided by the time period, which is going to be 2 pi divided by 97 times by 60 to convert it into seconds. So 2 times pi divided by 97 times 60, which gives you 1.079 times 10 to the minus 3. So we're going to get 1.1 times 10 to the minus 3 radians per second there. Okay. Calculate the radius of the orbit of the Hubble telescope. What information have we got? We've got that time period. So we know that GMM over R squared is equal to M omega squared R. So we know that R is going to, let's cancel the M, so we're going to take the R to the side. Gm over omega squared. We're going to want the cube root of that. So that's going to be the cube root of 6.67 times 10 to the minus 11 times by 5.98 times 10 to the 24, which is the mass of the Earth. And we divide that by 1.107 times 10 to the minus 3 squared. There. So let's calculate that. So we've got that number, so we square it. 6.67 divided by minus 11 times 5 times 5.98 10 to the power 24 divided by the answer gives us that. We want the cube root of the answer, which comes out at 6.99 times 10 to the 1, 2, 3, 4, 5, 6, which was going to be 7.0 times 10 to the 6 meters, two significant figures. The mass of the Hubble telescope is 1.1 times 10 to the 4. Calculate the magnitude of the centripetal force that acts on it. So what we've got R in the previous question, so we want to do GMM over R squared. So we've got R in the previous one, so let's square it to get R squared. The 6.67 times 10 to the minus 11 times 5.98 times 10 to the power 24 divided by R squared times 1.1 times 10 to the 4, which comes out at 8.967 times 10 to the 4, which is 9.0 times 10 to the 4 newtons, to two significant figures there, by putting in the values that we have for each of them. Alright. State in words how the force acting on a body is related to the change in momentum of the body. So this is Newton's second law, so force is equal to the rate of change of momentum. Okay. So we've got a football of a mass. It's kicked at 10 meters per second towards a footballer's boot, which then kicks it and shows how the force between the ball and the boot varies time they are in contact. What is the significance of the area enclosed by the line on a force time graph? It is the impulse, or the change, effectively what that means, the change in momentum. estimate the impulse that acts on the ball, stating an appropriate unit. So effectively we want to find this area. So let's count some squares. We've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, which kind of, I think these two add up to make 15, that one makes 16, 17, those two add up to give you 18, that one gives you 19, that one gives you 20, so 21. Basically, I reckon there's 21 sets of areas there, and each one of them represents 25 times 10 to the minus 3, because that's the base, and the height of one is 20. So let's see what that comes out as. 20 times 25 times 10 to the minus 3 times 21, which I reckon comes out at 10.5 Newton seconds, because it's an impulse that we've just calculated. Alright, let's move. Calculate the speed of the ball after it's kicked, assuming that it returns on the same horizontal line. Okay, so momentum before was going at 10 meters per second, wasn't it? And so initial momentum is 10 times by 0.42, which is 4.2 Newton seconds. And then the impulse of 10.5 is acted against the motion, so the momentum after is going to be 10.5 minus 4.2, so that's going to be a negative number, so minus 4.2, which gives you 6.3 Newton seconds, which means the velocity is 6.2 divided by the mass, which is 0.42. It's also 6.3. 0.42 gives you 15 meters per second to two significant figures, because all the data in the question is to two significant figures. And you might get a range of different answers for that one depending on your area, but you should get something around that. Okay, discuss consequences if the ball had approached the boot at higher speed but still received the same impulse. So in the initial momentum would be higher. Higher because speed is higher and mass is the same. But the change in momentum is fixed because it's the same impulse. Which results in a smaller velocity following impact, because essentially you're going to end up with a smaller velocity from impact if it changes direction. Or velocity stays in same direction now, so the ball keeps rolling towards the foot, which you would be a bit surprised by because that would mean it had gone through your leg. Or if initial momentum is sufficiently high. Okay, so that's what's going to happen. We're going to have a higher initial momentum, the same impulse acts on it, so it's either going to have a smaller component of velocity if it still changes direction, or it might even keep going in the same direction because it has sufficient momentum that is bigger than the impulse. Okay, so let's move to the next question. Alright, so we've got well, essentially we're looking at a ball rolling down a slope, but we're using a capacitor as a method of measuring that time. We've got two switches which get essentially opened by the ball as it rolls. Describe the procedure that it should use, including the measurement when using this arrangement. Explain how use the measurements taken to calculate the acceleration of the cylinder down a slope. So essentially the capacitor is being used as a method to find the time. So the first thing we want to do is measure the initial V across capacitor, because you want to know what the starting potential difference is, and you want to know the length of the slope, because we're going to use essentially a distance and time type thing. Then you're going to want to let it roll and measure the final V across the capacitor. And what you're going to do is you're going to use this equation here to calculate T, because you know Vt, you know V0, you know R, and you know C, so you can use that to calculate the time it takes to go between those. And then essentially what you're going to do is you're going to use S equals half AT squared, so you can then calculate acceleration, because you have time and you have measured the displacement already. Repeat let's say repeat 3 times, calculate average time, because that's going to allow you to reduce any random error in your results. So then you'd essentially get a value for the acceleration that was proved to be like a more reliable and accurate, because you've reduced the random error. So that's the way we'd go about doing this experiment. When the students set up the experiment, you've got a certain capacitor, a certain resistance, and we've got some values for that. Calculate the time taken, so we're essentially using this equation here, and we want to get the time, so we're going to have Vt over V0 it's going to be log of minus log of Vt over V0 dot RC. So let's put our values in there. So the final was 5.8 divided by 12. Log of that answer is minus 0.7 whatever times minus 1 times by R, which is 200 times 10 to the 3 times by 22 times 10 to the power of minus 6 gives you 3.5 0.199 dot 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 dot. So essentially 3.2 seconds. What if we assume acceleration is constant? What value does that give you? So we knew that s equals half at squared. So a is 2s over t squared. So we were given the distance earlier, which was 2.5 meters. So we're going to have 5 because it's 2 times 2.5 over 3.19 dot 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 squared. So let's do that. So let's square our value. 5 divided by answer is 0.4885 dot dot dot. So it's going to be 0.49 meters per second squared to two significant figures. Okay, let's move on to the next. We've got a polystyrene ball suspended between two metal plates. So we're going to get a uniform field going on here. We've got a separation of 80 millimeters and we've got a charge of the ball. We've got the potential difference. Calculate the field strength between the plates, assuming it's uniform. So field strength is V over D, so it's going to be 600 divided by 80 times 10 to the minus 3, which is kind of 600 divided by 80 times 10 to the power minus 3, because it's in millimeters. It gives you 7.5 times 10 to the 3 newtons per coulomb. You could also have given it in volts per meter, which in fact they have there. Show that the electrostatic force is 1.3 millinewtons, so F is the field strength times Q, so it's 7.5 times 10 to the 3, and the charge was minus 0.17. Was it nano? Micro coulombs. Equals minus 6 minus 1.275 dot times 10 to the minus 3 equals minus 1.3 times 10 to the minus 3 newtons, or minus 1.3 millinewtons. It wanted the magnitude, so we can just cancel out all these minus signs because we're not interested in the sign, we're just interested in the magnitude. Alright, let's move on. Because of the electrostatic force acting on it, the ball is displaced, and we've set up a pendulum effectively. Label the forces that act on the ball when it's in this position. So we've got the weight force acting vertically downwards. We'll have some sort of tension in the string which is holding it up, and we're going to have an electrostatic force, that's going to be acting on it there. Okay, so determine the mass. You've got the mass of the ball. Calculate the value of theta. So you know that t sine theta is equal to the electrostatic force there, and we also knew that t cosine theta is equal to W. So by dividing the first equation by the second equation, the t's cancel to give us tan theta is Fe over mg. So that, let's put in the values for that. So what did we have for the force? I think it was like 1 point. So the force I think was that is 1.3 times 10 to the power of minus 3 divided by 4.8 times 10 to the power of minus 4 times 9.81, which gives you 0.276, and inverse tan of that gives you 15.43 dot 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 is 15 degrees. So the two significant figures there. Alright, final question. We've got some magnetic fields and probably some induction later on, no doubt. That don't have too many papers without the induction. Okay, state the direction of the force on the wire when there's a direct current from P to Q as shown in the figure. So the field is going from north to south. The current is going from P to Q. So therefore, using Fleming's left-hand rule, it's going to be down. In a second experiment, an alternating current is passed through the wire. Explain why the wire will vibrate vertically. So the current's either going from P to Q or Q to P. So the field is always from north to south. Current is either P to Q or from Q to P, because that's what's happening when it's alternating, it's just changing direction. So then the force is perpendicular to both, and so changes between up and down. So those are the only two directions of the force. And the magnitude of the force varies with the current. So the higher the current is, the bigger the force is going to be that acting on it, but then it's changing direction as well. Okay, a permanent magnet produces a uniform magnetic field of flux density 1020. So we've got B, so we've got L, and we've got I there. So we want the maximum force, so we want the peak current, which will be 2.4 times by root 2. So you do have to remember your things from your AC circuitry here, which is 3.39. Turns that F max equals B I max L. So it's going to be the I peak times 220 times 10 to the minus 3, and times by 55 times 10 to the minus 3, because it's in millimeters. 0.041 which is approximately 0.041 newtons, which is approximately, 0.040, which is what we were trying to show is, roughly speaking. Okay, so the length of PQ is 0.4 meters. When the wire is vibrating, trans waves are propagated along the wire at a speed of 64 meters per second. Explain why the wire is sent into a large amplitude vibration when the frequency of the AC supply is 80 Hertz. So first, let's have a look what we've got. So we've got a velocity and we've got a frequency. The wavelength of those vibrations is V over F, which is 64 divided by 80. Let's calculate that. 64 divided by 80, which is 0.8 meters. And so therefore what we've got is the wavelength equals 2L. So what we've got essentially is we're forming the fundamental mode of vibration. Resonance as it matches the natural frequency as a fundamental mode of vibration or a first harmonic is formed. So this is actually a mixture of resonance and stationary wave question here. So the key things going to be looking for here is showing the wavelength is 2L, so we're causing resonance because it's at the natural frequency, and what you've got is the fundamental mode of vibration or the first harmonic. And that concludes this paper.